Hello, my name is Harshil Bhatia and I will be presenting quantum cycle-consistent quantum hybrid matching of multiple shapes. Multi-matching is a problem of finding shape correspondences between several shapes. When this is solved in conjunction with cycle consistency, it helps improve the reliability of the results. In our method, we follow the following approach. Given a shape collection with initialized correspondences, we select an anchor and two shapes S1 and S2. This is fed into a 3-shape formulation which optimizes the correspondences on a quantum annealer. This provides us with the updated correspondences. This is then repeated for the entire shape collection. To optimize for 3 shapes, we start by constructing the energy formulation. Then cycle consistency is enforced by parameterizing updates to the permutations. Post this, we cannot formulate it as a quadratic unconstrained binary optimization problem, which is a prerequisite for the quantum annealer. We apply approximations to convert it to a QUBO, and then it is optimized on the quantum annealer. Moving on to related work, we will be focusing on non-learning based methods which, similar to our method, can generalize to unseen datasets. Zoom out uses spectral upsampling to reduce the dimensionality of the problem. However, it only works for 2 shapes, which limits its applicability to more complex shape matching tasks. This idea is extended to multiple shape by isomush, which jointly optimizes point and functional correspondences for cycle consistency. This method has shown promising results in shape matching tasks and is the current classical state of the art. Research has been conducted on graph and mesh alignment problems using quantum technologies. Initially, quantum graph matching was proposed, which was the first to solve matching problem using adiabatic quantum computing by formulating them as quadratic assignment problems. They proposed a formulation that optimized their QAP over permutations. QSync addresses the problem of matching multiple shape. They solved this problem by synchronizing permutations of the graph. Both of these methods were severely limited in their ability to handle large instances. QMatch improved on these works by proposing a method that scaled up to instances with 500 vertices. They achieved this by parameterizing updates to the permutation matrices between the 2 shapes. We build upon their work and extend their method to handle several shapes. Preliminaries. First, we formulate shape matching as a quadratic assignment problem. Given 2 discretized meshes NMN, we need to find an optimal permutation between each vertex. To achieve this, we minimize the energy E of x, where x is over the set of permutation and W denotes the energy matrix, which can be constructed using geodesic distances. This problem is NP hard in nature to solve. Adiabatic quantum computing is an optimization method that solves NP hard problem class of quadratic unconstrained binary optimization. Here we give the annealer a binary decision vector. The annealer embeds the problem onto quantum hardware and performs an anneal, which results in the minimum energy solution. The energy minimization that we have previously discussed is not a QUBO. QMatch proposed that instead of optimizing over the permutations space, we can model updates to the permutation using cycles and optimize over them. This parameterization is linear in decision variables. This is termed as cyclic alpha expansion and transforms the formulation into a QUBO. Other contributions of our work are as follows. We propose a new hybrid quantum method for multi-shape matching with guaranteed cycle consistency. Specifically, we propose a new formulation of the optimization objective for the 3-shape case that is mappable to modern quantum annealers. This formulation is then extended to address the N-shape case, where our method is linearly scalable in the number of shapes. To solve for 3 shapes, we can use the 2-shape energy formulation and apply it to all possible pairs. Additionally, the constraint of cycle consistency is also enforced. Naive approaches to solve this would be, we could apply 2-shape matching for all possible 2-shape pairs individually. This is not cycle consistent and scales quadratically. We could also fix an anchor shape and then find correspondences through that anchor for the remaining shapes. This is cycle consistent but doesn't use all the information present in the dataset. Additionally, it causes accumulation of errors in any 2 shapes that do not involve the anchor. To enforce cycle consistency, we instead parameterize updates to the 3rd permutation via decision variables associated with the 2 constituent permutation. This results in cubic and biquadratic terms in the energy formulation which violate our problem type of QUBO. To deal with this, we make approximations. After several considerations, it was found empirically optimal to ignore cubic and biquadratic terms. This is due to the innate sparsity present in the terms responsible for producing the higher order terms. Once we have made this approximation, we can formulate the problem as a QUBO. We optimize our objective iteratively. In each iteration, we choose a subset of vertices and construct cycles from them. This is done because considering all vertices and choosing all possible combination cycles is highly inefficient and not feasible. After this reduction, we construct a subsampled W matrix which only contains the weight terms of the cycles involved in the current optimization. This completes the optimization formulation for the 3 shapes. This is then extended to n shapes as follows. We choose an anchor using the heat kernel descriptors. Once the anchor has been decided, we iteratively optimize randomized triplets using a 3-shape algorithm, which is treated as a black box. These iterative optimizations facilitate information flow. We observed an increase in quality of correspondences in 3 shapes when optimized for a larger n-shape instance. This process is repeated until convergence. As for our experimental results, we outperform all quantum state-of-the-art and are at par with classical works. Our method gives more correspondences with low errors as depicted by the PCK curves and the area under those curves. We note that these results are using simulated annealing, which is a classical counterpart for quantum annealing, as instances of this site do not produce high-quality solutions on the quantum hardware. We now compare the performance of quantum annealing and simulated annealing. We consider a reduced setting with smaller cycle set. From the obtained PCK curves, we observe similar performance for both the solvers. Our method is linearly scalable with respect to the number of shapes and guarantees cycle consistency. This figure depicts qualitative results for shape matching performed on 100 shapes present in the Faust dataset. Here are more qualitative results on the Centaur class of the Tosca dataset. To conclude, first time in the literature, we observe the scalability of quantum methods and depict results that are comparable to the classical state of the art. Interestingly, approximating certain higher order terms still allow for high quality solutions. Iterative optimization of triplets is effective in carrying information and can benefit classical methods as well. Thank you for tuning in. Please visit our project page for more details.